I want to go through quickly some key formula and terminology in probability and statistics that you will encounter. I'm not going to make direct connections to language technology or AI, but you will see some examples from language. And I'll leave it to you in other videos and in your reading to make those connections. But I want to provide a video for those who haven't run into these terminologies, forgotten them from high school, or perhaps is familiar with them individually but haven't made the connection of them in a logical sequence of how you put them together to build something like we do in AI. The first one we are going to look at is the probability of events that are dependent, where the contextual event influences the event that we're interested in figuring out the probability of. And that's called conditional probabilities. And this is the formula. And this formula interpreted means what's the probability of A, the event I'm interested in, predicting in the future, what's the probability of it occurring given that B has occurred? So in the context of B, that's another way of saying it. To figure that out, you figure out the joint, this is called the joint probability of A and B co-occurring, and you divide it by the probability of B occurring. This symbol right here is sometimes referred to as intersection. It's the probability of A and B intersecting. And one reason that we use that is because you can illustrate that formula with Venn diagrams. So here we have a sample space that is the context, the full context that we're interested in. And within that, we want to know what's the probability of A given that B occurs. So we need to figure out, to start out with, to do anything, what's the probability of B occurring, what's the probability of A occurring within the context. And we know how to do that. You count previous occurrences of the phenomenon you're interested in and divide it by all possible occurrences. So in this example, we're asking the question, what's the chances I'll miss my flight A if my connecting flight B is late? So in that case, my sample space is likely to be, well, it could be several things. We can go through them, but let's just pick one that seems relevant. It could be the sample space where both flight A and flight B, all their flights, so when they occur at the same day, or all their flights. Either of those could be, so all their flights, whether or not they occur on the same day, either of those could be sample spaces that might be useful for us. So to get the probability of A, we're going to count the number of times, actually, sorry, I said flight A. What I meant is people missing flight A. So we're going to count the number of times that people miss flight A out of all the times, say that flight A occurs. How would you get that? Well, practically speaking, I don't think the airline's going to share that with you. They may not even know. You could put out a poll on the internet, maybe interview a bunch of people. Somehow get that information, get all the data you can, do the counting. And in this case, it turns out that it's a 4 to 10 or 0.4 or 40%. So whether or not 100 people missed a flight or there were 100 flights and people were late on it 40 times, or whether there was 10 flights and people were late for it 4 times, I don't know. The ratio is the same. The probability is the same in either case. For the probability of B, what's the probability of flight B being late? That's our B event. Same thing. We'll count up all the times that flight B was late in the context of, well, all flights, all the times that that flight occurred. If we want, we could narrow it down to all the times that flight occurred when these particular pilots were flying to give us a smaller context space. But again, that's going to be determined by the question you want to answer and what seems useful or what data you can get a hold of. So we could probably look at, say, the records from the airport. Those are public, to see the flight status over time for this flight. And then we have that probability. Now, again, our question here is what's the chances I'll miss my flight A if flight B is late? So in the context where those two things are happening. So, and this is where you can think, well, why can't we just calculate this intersection here, right? That's what we're interested. What's the probability of those two things happening together? People were late for their flight A, and flight B was late at the same time. That is your joint probability. The problem with that is, I mean, in some cases it might be the same number if all the time that somebody missed flight A, it was when flight B was late. In that case, this might be the same number, but there's other reasons why people might be late for flight A. It might be they were on another flight. It might be that um, they got to the airport late and so on and so forth. So this co-occurrence, just a simple co-occurrence, is not going to be a good enough model of the events for us. But we can use this because we are trying to get into it. So we're not interested in the time when these things just happen to co-occur together. We're only interested in it in the context of this bigger context of flight B being late, right? So we don't care about this. So all the times that people were late for in times when flight B wasn't late, we don't care. So that's why the joint probability here is not going to be good enough. Now notice I was very careful not to say that we're looking for times when people miss flight because flight B was late, because we can't model that easily. We'd have to get very good, really good data to be able to say that. And generally speaking, that's not easy. So that's why we're using the word given, right? This thing means given. It's nice, a little way of not committing ourselves to causes or reasons. So since this is not enough, there's lots of reasons why people might be missing flight A. That's why we have to do this division. So this division, when you have something underneath this division formula, you could think of it as saying out of. So out of all the times that flight B was late, that's why we have the division. That's what we're interested in. Great. So what about this? What about this one right here? What is this? This is the co-occurrence. That's nice, fine, but how do we get there? How do we calculate that? Okay, so that's our next formula and concept, which is joint probability. And just a quick review here. What this thing is saying is what's the probability of the co-occurrence of event A and event B divided by the number of times event B happened. And notice that we interchange here probability and number, and you see that number or count sometimes. And this is assuming that you remember that the basic thing we have to do is count the occurrences divided by the context. And so yes, you have to do a probability here, not a number, but you often hear people kind of skip over it and kind of assume that you know that there was a division that happened here. It was a counting and not a strictly a count. So counting and then dividing. So just kind of heads up on that. All right, so how do we figure this out? We know how to figure this out. This is simple probability, count and divide. How do we figure out these two things likely happening together? That is joint probability of independent events. And it's the same way that you figure out weighting. I'm just going to throw out that term right now and not explain it because for the most part, I just want you to see that you can have terms used differently in different contexts, but how you calculate them or think about them, well, maybe you think about them differently in different contexts, but how you calculate them can be the same. So we'll just talk about joint probabilities. And you may have seen, right, so this is the intersection symbol. You may have seen the same thing written as the probability of A, joint probability of A with B with a comma. And that's the same thing. There's a little equal sign. This is the same thing. It's two ways of writing the same thing. It's like British English and American English. You can spell words, same word in different ways. Well, first of all, we have to figure out the probability of A occurring. We know how to do that. We count and divide, and we saw that. We had that. If you wanted to calculate it for the flights, we had that. We already talked that through. I need to know the probability of B. Okay, so first of all, you need that. But once you have that, then you can figure out the joint probability. And how you do that? Oh, well, it's super hard. You multiply. No, that was sarcasm. It's not super hard. You calculate the probability of A, simple probability of B, and you multiply them together. And that's it. Breaks down to a very simple calculation. So going back then to our example, we would first calculate, right, the probability of A, probability of B by getting our data from the internet or from the flight status and dividing. We could then take those two, multiply them together, and that gives us this right here, expressed in this formalism. And then we divide it by, right, this, we just divide it by this, which we've already calculated. So we can do that. So what's the chances I'll miss my flight A, if my connecting flight B, is late? Formalize it with this, and we've calculate the probability of A and we've calculated the probability of B, so now it's just a matter of plugging it in. So the probability of missing flight A, given that flight B was late, we are going to plug in this formula here, and I will just go ahead and put in the numbers. So probability of A is 0.4, and the joint probability would be multiply that by the probability of B, which is 0.2, and then we're going to divide it by the probability of B, which is 0.2. So you can get a calculator or you can do it in your head. If I write this correctly and don't forget my zeros here, the top is 0.4 times 0.2.08. I think I might be missing a zero there. You can check me on your calculator. I'm doing this from memory real quickly, so I don't waste your time. Divide it by 0.2, and the answer there, and I know this is correct, is 0.4. So what's the chances of you missing your flight A if flight B is late? Well, 0.4 or 40%. You got a 4 out of 10 chance or a 40% chance that you're going to miss your flight if the first flight is late. Well, how might this be useful? Well, let's say you're trying to figure out which ticket to buy. You've got a bunch of different flights you can have with different connections, different places, and different amount of times between the flights, and which ticket is best? Well, if you can get the information, do the counting, and then do these calculations, then you can figure out the number for the ticket with this particular flight, with people missing it if the first one is late, and then you could do the same calculations for the different ticket where, let's say, this one, I don't know, this one lands in, let's say flight B lands in Houston, right? And then this is people being late to the flight onto Orlando, which is where I usually fly into. But okay, so we get 0.4, and then you can say, well, let's do the same calculations here, use the same formula, but now I'm going to look at the cases where flight B, the one I'm interested in, whether it might not be late. Let's say that connection is in St. Louis, right? And then my next flight is a different flight, but also going to Orlando. So I can calculate that, and let's say I go through all of it and I come up with, I got the probability here, it would be different, probably probability of the first flight being late. I plug it into this formula, and let's say I come up with 0.1. So then the answer to my question is, what's the chances of missing my second flight if the first flight is late? Well, in my second ticket, the chances is 0.1, 1 out of 10, or just a 10% chance that I'm going to miss it. That's a better probability. I think I'll buy that ticket. And that is having to calculate for both of those possible tickets and then compare is all of what you did to make a good choice. But that's only with that one factor of whether or not the previous flight is late. What other factors or contexts might we want to model here that would influence whether or not we are likely to miss flight A? Well, flight B could be late. We calculated that, but we could also calculate, well, what if flight B is late and it's very far down the concourse? The gates are very far from each other. What if those two things happen together? Compared to what if flight B is late, but the gates are right next to each other? Those two happen together. Let's calculate those two factors happening together and compare them to these other two factors together. In this case, we only have one factor, one thing that might influence the outcome. If we want to add more, that would be useful to model. How do we do that? So that's going on to our next concept here, which is the chain rule. And this comes into play when you have you want to figure out the joint probability of a lot of factors happening. So that then you can maybe go on and calculate the conditional probability, right? Because you need the joint probability. Here we have the comma instead of the intersection. You need that joint probability in order to calculate the conditional probability, as we saw. So how do you do that? Well, fortunately, you don't have to figure it out because we have this thing called the chain rule. And this is the formula for the chain rule. So what this is saying is if you have a bunch of joint events, things that you need to figure out the probability of, this is the simplification of the formula. I'm not going to walk through it. Just if you're not familiar, this big pi, a Greek pi, says the product of the product. So you're going to do multiplications, and then you're going to multiply them all together, basically. So actually, it looks scary maybe, but it's actually pretty cool. So just telling you, all this comes down to is a bunch of simple multiplication stuff you learned in grade school. So it's really not that hard. You just have to follow the formula. All right, so what is it saying? So this is the better breakdown right here. It says start with the first one and figure out the probability of, right, the first one happening. It could be any one because these are joint, they're independent of each other. So technically it could be any one that you chose. We could start with A, just because we listed it first. And we know how to figure out the basic probability. Count past occurrences, divide by context of interest. And then what you're going to do is, even though these are independent of each other, as we saw indicated by this joint probability, we're going to pretend like they're dependent. And you're going to calculate the conditional probability of the second one, which could be B. We could just grab that one. The conditional probability, what's the probability of B occurring given that A has occurred, right? So even though joint probability, when you see these commas or the intersection, you should assume independent. They're not conditioned on each other, not dependent on each other. In order to figure out the probability of that independent co-occurrence, you have to break that down and pretend like they're conditioned on each other. That's just how it works. That's the chain rule. All right, and we know how to do it. That's great. All right, you don't have to learn anything new. We already walked through the conditional probability. So what's the probability of the second event occurring given that the first event's occurred? Then what's the probability, all right, we multiply that, those two together, and then we go on to the next one. What's the probability of the third event occurring? So that would be, all right, so there's our conditional probability, right? We're going to plug that in. What's the probability of the third event? So let's say we treat C as a third event, given that the previous two events have occurred. And here you should start seeing a repeating pattern, because here, once again, we have multiple, well, we have a joint probability, right? Well, we know how to figure that out, both because we know how to figure out joint probability and also because we have the chain rule right here. This tells us. So we actually have to plug in the chain rule again at this point and plug it in and then do the multiplication of this one, this thing, and this thing here. So the chain rule actually comes in at different layers. But we know how to do this. There's nothing new here that we haven't already covered. It's just a matter of putting them in the correct order. We have the probability, and then we have conditional probability. And then we have joint probability. So we can do all of those. And we just go on from there until we've plugged in everything for all the factors that we're interested in. So we could look at an example here, how to compute the probability of W, and W here is standing for, in our case, a sentence. How do we compute the probability of this sentence occurring? Another way of asking that is, how do we calculate the probability of all of these words occurring together? So I have it here as a joint probability, but just to be clear, don't get confused by those commas there in the formula. Let me write it and get my pen to work here. There we go. Our sentence is this. It's water is so transparent. Perhaps we're talking about a pond, although it wouldn't be any pond that I've seen in Florida. So more likely we're talking about a spring. Its water is so transparent. How do we compute the probability that this sentence occurs? Well, again, we got to have a lot of data. We're going to have to count and divide. So it's really great if you just start calculating the probability of each of these words occurring. That's going to be the first step. Out of all the words that you have in your data, it's great if you create a table and just plug in those numbers, and the rest of it will be easy because, of course, as we can see, to do that, it's a joint probability of a lot of probabilities of these individual words here. So we got to plug in the chain rule. And the chain rule, you can go back to the slide, but, well, actually, here it is right here. Don't you have to go back to the slide? I put it there at the top for you to see. So here's our sentence here. Here I wrote it as a sentence, but we talk about that as a joint probability with a comma between each of those words. And the chain rule tells us, all right, when you want to know what the probability of this sentence occurring, first figure out the probability of the first word. We can do that. Count the number of times it's occurred, divided by all the words in our database. Then calculate the probability of water given its. And here we cheat a little bit. So here I'm making a little direct connection to language technology. In reality, this says, what's the probability of water and its occurring? So what's the probability of water occurring in the context of it? So that could be a string of water, its. It could also be a string of the context, its water, in either order. So in reality, that's what this is saying. You need to count all those occurrences. So the reality of the formula is telling this. The practicalities of language technology is that we only look at the string. Sorry, that's not right. That's the wrong two words. We only look at the string in the order we're interested in. So we're only going to count the number of times that this particular string in this order occurs out of all pairs of words in the data. Now, that's kind of cheating really, because that's not what our formula tells us to do, but it works, so we do it. And I also would note here, it works particularly in the context of English, which has a strict word order. It's not necessarily going to work quite as well in other languages that have free word order. So these are things that you have to take into consideration when people say this is how you do it. And you say, yes, but you figured out for English. What about the other languages? It might work, but you got to test it. All right, so there's a quick connection to practicalities and realities of language technology, but we're going to go back to just looking at this example as a kind of a math thing. So we know how to calculate the probability of its. We have our conditional probability formula to figure out the probability of water given its occurring before water, as it happens. And then we go on to the next one. What's the probability of is given that the previous two words is its water? So again, this is where we go back to our chain rule. So if you have a joint probability here, you can go back to the chain rule, and this would say figure out the first word, its, and the probability of the second word occurring given the first word. And then the probability of the next word occurring given the previous word is something that you could break it down into, which is nice because we already figured out, right? We already figured out that. We already know the number, if we just plug it in, we already figured out that. So all we have to really do is calculate this and plug it in, substitute for that. And we go on. Same thing here, right? Now we have three words. And again, we're going to plug in the chain rule. So we're going to bring all of this down and plug it in, substitute for that, and then add on the probability of the last one, which in this case is a probability of so given is. And then we multiply them all together, and then we go on to the next one. And again, the chain rule will allow us to substitute in all those numbers. So we break it down. As you can see here, everything is getting broken down. Despite the complexity of that formula when you first glance on it, it's all about joint probability, simple probability, and conditional probability. You really don't have any other tools that you have to work with. So that's an example. And this is used in language technology. Well, we'll see that. Because I want to move on to our last concept. So we've covered conditional probability, joint probability, chain rule when you have multiple independent events that you want to calculate a joint probability for. And we've seen an example in language. Before we move on to the last concept and term that I want to cover, let's think about this a little bit. So we want to calculate the probability of a string of words. So this particular sentence, let's say it continues. That wasn't the end of the sentence. It goes on and it says, its water is so transparent that. And let's say you're a generative AI and you want to be able to come up with a good, likely English sentence. So what's the probability that the word I should put after that is the? So given that the first words of the sentence are those six, how likely is it that a good word to spit out next would be the? And the simple way of thinking about this is back to our basic concepts. Of course, it's more complicated. We just walk through this, but basically, what are you doing? You're counting the occurrence, the phenomenon you're interested in, which is this full string, its water is so transparent. That, the, out of the context, which in this case is the previous words, divided by how many times does its water is so transparent that occur. So that's simplification of what we just walked through. And you saw how complex, well, at least how long the chain rule can be. So the question is, do we want to run the chain rule for this full phrase or any sentence, no matter how long it is? The answer is no. That is too many calculations. The reasons why that gets to be too many calculations, why is that a problem? Because every calculation, no matter how fast the computer does it, in our mind, it's still going to slow the computer down a little bit. It takes, fractions of seconds add up. So it's too many. For one thing, sentences can get long. More to the point, there's too many possible sentences. We're never going to see enough data, even the whole internet, because we're always inventing new sentences. So there's never going to be enough for us to be able to accurately estimate the possibility or the probability that the is going to follow those particular six words. Those particular six words, it's what is so transparent that. I'm sure they have occurred more than once in written English somewhere that we could grab from the internet, but it's just not enough. Even with trillions of words, the creativity that we have in our language is not going to provide us with enough data to calculate the probability and have useful predictions for future writing. So, with that practicality in mind, we can introduce our last concept, which is Markov's assumption. And he's a great guy because he figured out that there's a simplification you can make an assumption here. It may not be true, but if you make this assumption, it's workable. And that is if you have a lot of factors, so you have a lot of factors, a lot of things, or in this case, a string of words that you need to calculate the joint probability for in order to figure out the probability, the conditional probability of the next thing, you don't have to do all those calculations. It turns out if you just look at the previous word in this particular example, so you've just looked at one of those contextual or one of those factors that we're interested in, the previous word here, you're going to get a number that is pretty close to the number that you would get if you ran the chain rule on all that whole string and calculated every single one of it. And even if it's not close enough to actually come up with a workable or a useful tool, you can go a little bit further and still keep it simple, which is maybe slightly better numbers for predictions would come out of just looking at the previous two words instead of just the previous word. And if that's not good enough, they look at the previous three words, the previous four words. All of those are less than looking at every single word that happens in the string. If your sentence happens to be 30 words long, 3 words and 4 words is a lot less. So the question you might come up with is, okay, this is a nice assumption. First of all, does it work with language technology? Yes, it does. Second of all is, well, how simple should I get? Is one word enough? Is the previous 2 words enough? And it turns out that one word, the previous word's not enough, but actually once you get past looking at the previous 10 words, it starts not to be useful, which if you think about the average length of a sentence, at least in English, where most of this work has been experimented with, that makes sense. They don't tend to average much longer than 10 words, and then what happened in the previous sentence doesn't really affect the next sentence as much. So one word's not enough, just look at the previous word. 10 words, beyond 10 words, it's not really helpful. The ideal, the most helpful, a perfect balance between usefulness and minimal calculations is looking at the previous 2, 3, and 4 words. And so Markov's assumption is very helpful for us in language technology. And there you have it. All right, I made a quick connection there to language technology. That's great. I wrapped that up. But the point of the video was to cover the formula and the terminology that get thrown out when people explain these. And so what did we cover? We covered conditional probability, joint probability, the chain rule, and Markov's assumption. So with this, hopefully some of the other videos and the reading will make a lot more sense to you.